So last time I think we finished off by talking about affine subspaces and then hyperplanes, and we defined hyperplane as just the solution to a linear equation, inhomogeneous, and then that was the affine hyperplane. And then we talked about a half space, which is partitions. Basically, a hyperplane partitions a vector space into three pieces, the places where the inequality is positive, negative, and equal. Okay, so that will put us in a position to talk about convex bodies. So the idea is that a subset K, so of a vector space V is convex if and only if for every x and y in K, then lambda x plus 1 minus lambda y is also in K, where lambda is in 0, 1. So in particular, if you have a set of VI that are a subset of K, then any I lambda I VI is also in K as long as lambda I are greater than 0 and sum I lambda I equals to 1. So in particular, we can understand that the subset I is a set of indices, in this case maybe a finite set, and then you have that the corresponding lambdas in the convex combination are precisely, and so this thing would be called a convex combination. It's just like an affine combination, but we're restricting the coefficients to be non-negative, and we can interpret this as a probability distribution. So there you start to see that convex bodies are very much related to these operational notions. Probabilities sort of show up naturally here. Okay, here's a little would you say that okay, so we already answered the affine version of this, so I won't stress you guys out. If I have K1, K2 are convex, then K1, K2 is also convex. And the idea is pretty simple, that any point that's in the intersection, well, their convex combinations must be in either K1, which is convex. So already you have that those points are inside of here. So the intersection is also convex. And then you can say that you can define the convex hull of, so the convex hull of some set X of V is the, well, you can just define it like this. I will use the intuitive idea first, actually, is the smallest convex set containing x. And this ends up being equivalent to the notion that the convex hull of X is defined by all convex combinations. Maybe I should put it like this, X for X in X, because X need not be finite. So X such that lambda X greater than 0 and some X in X lambda X equals 1. So when I say the smallest convex set containing X, basically I'm using this fact that I take any convex body which contains X, and then I take their subsequent intersections, and the maximal set of intersections for all sets containing X is going to give me this convex hull. So maybe just a couple of facts, so the convex of X has to be a subset of the affine hull. It seems clear. The dimension of the convex hull of X is equal to the dimension of the affine hull. So I will just quickly write this down and I'll get rid of this. But remember, I had this line here, and the affine hull of these was just this. And then, so this is a one-dimensional affine subspace, and then the convex hull is just this part of it. So in particular, the dimension will just be the same. Okay, so I have the following, let's say, lemma here. H plus prime subset V are half spaces. Show that H plus is convex. And I guess this part is trivial because of this, that H plus intersection H plus prime also convex. Okay, maybe we don't care so much about the second one. So any idea how to prove the first part? What would it mean for this subspace to be convex? So remember, this is a good model to have in mind. We have something like this. A half space is going to be something like, take this and everything below it. So this is H, and then the line including everything below it, say this is some y is equal to b, then the h is, this is the h, and then h plus is all x, y, y such that y, I guess, greater than or equal to b, so I did this the wrong way. Let's do this. So it's going up. And so what would it mean for it to be convex? It means that I take any point in here, and show that there's a line between them. So it's going to go something like this. Let x and y be in H plus, then we say, okay, well, is it the case that, so an inequality is going to, this half space is going to look like this. We have the inequality sum I alpha I xi greater than or equal to b. So now this is for x. It satisfies this. So now we're going to ask whether they're a convex combination. So alpha I of lambda times xi plus 1 minus lambda yi. Let's compute this. We're going to use linearity, and we have lambda times xi alpha I xi plus 1 minus lambda sum I alpha I yi. And we want to show that this thing is greater than equal to b. It's not hard to see that this piece is greater than or equal to b, and so is this one. So this whole expression will be at least, let's see, let the value of the one be, this thing will at least be, so if this is bx, and this is by, then this thing is at least greater than or equal to, and both of these are greater than or equal to b. Then what we have is that this is at least greater than or equal to lambda, and we take the minimum of these, lambda times the minimum of bx by plus 1 minus lambda, the minimum of bx by. These are the same value, so this will sum to just the minimum of bx by, which has to be greater than or equal to b. Yeah, this part was maybe a little bit fast. The linearity part is probably okay. Is this okay? Getting to this part? Okay. And then here's sort of the trick. I mean, because these things are not equalities, like I would like to be able to say, oh, if this is b and this is b, then it's the same value, and then lambda b plus 1 minus lambda b is just going to give me b again. I would like to be able to say that, but that's not necessarily the case. All we know is that these are inequalities. So what am I going to do? I know that both of these are at least greater than or equal to b, and just give them a value, bx and by. This expression has to be greater than or equal to when I replace these by the minimum between the two. But once I replace the minimum between the two, and the fact that these are non-negative is important, so I can't actually go over that value. So then I have the minimum, and then these sum to the minimum. So that means that these half spaces are convex bodies. And then this result over here then tells me that the intersection of these half spaces are also convex. So in particular, if I have this two-dimensional coordinate plane, and I start cutting this thing up by, yeah, so this piece, we know individually that x and y are in this set. And that means in particular that they are greater than or equal to b. and say that the value is actually bx. Well, there's a question mark here. I'm asking, yeah. I'm saying, is this equal to greater than or equal to b? And that's what I want to show. Yeah, it's not very visible, sorry. Question, maybe still not visible. Anyway, my apologies. Yeah, so it's just asking the question, is this greater than or equal to b? And then we show that it is. So what this tells us is that, say I have this two-dimensional space here, and I start cutting it by half spaces. So I cut it here, which is including everything here, say, and then I go on, I cut it this way, and now I include everything here, and I'm just including this region right here. And then you can keep on cutting these things. And what you see is that this is a convex body. And as I continue to cut these things, I sometimes develop these corners, like right here. And this thing is going to be called a vertex. If I just keep on cutting by half planes, and maybe I cut by another one, say right here. So now I have one right here. And then so I develop these corners. And so you start to see that as I continue to cut these things, I develop these corners. These are edges. These, you can think of them algebraically as, what am I doing? I'm inserting a set of linear equations. So the boundary of this thing is precisely a linear equation. So I'm getting these corners precisely when I have a solution to the set of linear equations that so when I intersect these half planes, I'm basically adding a new linear equation to my set. So then this is how you start to get these things called vertices. These are the extreme points of my convex set. And this is sort of a little bit of a flavor of how there's this thing called the Minkowski-Weil theorem in convex geometry and sort of like discrete geometry. And it just basically tells you that the H representation of a polyhedron, which is given by intersecting these hyperplanes, is equivalent to the convex hull of a set of points, vertices if it's a bounded thing, or points and rays if it's a non-bounded thing. Like for example, if I had just had this, then there will be no vertices, but the Minkowski-Weil theorem for polyhedra still holds. And it just basically tells me that the space is generated by convex combinations of rays, and the rays can be infinitely just go in this direction. So it also works for these unbounded things, but a lot of times we're going to be interested in things that are bounded. So they're going to be called either just convex sets or bounded convex sets and or polytopes. Okay, yeah, so let's look at the assignment, the practice problems. Anyone get a chance to look at these? If we could bring up the problem set or the assignment sheet. So I guess maybe. So when we're looking at these practice problems, the first one is going to be something like, I defined this thing, which is called a probability simplex. And so we'll show that it's a simplex. Element of Rn such that pi greater than 0 and some I pi equals to 1. Okay, so the first part is okay, so I will not say that it's obvious, maybe it's not. So is it clear that this is a convex set? Okay, so without too much work, I could take certain extreme points in Rn, and it would always give me precisely something of this form. In particular, say take the coordinate basis, the Cartesian basis, and then so basically ones and everywhere else 0. And if I use my linear combinations such that their coefficients are always non-negative numbers and they sum to 1, well, that's a linear combination that's also a convex combination, and you will get always something of this form. So this is a convex set. Too hand wavy? I just was a little too lazy to write everything out. Okay, so I guess that also does part B of this thing. So, explain. And what this is making me realize is that I did not actually explain what a simplex is. Let x be finally independent. Affinely independent, do you guys recall what this one means? So the way to think about it is if I have something that's like this, what I want to be able to do is to say that I map this thing to the origin, at least one of them to the origin. And then I want to say whether the other remaining points are linearly independent. So a set is affinely independent. So x is affinely independent if and only if x minus some, maybe say v is in x, is linearly independent. So then what is a simplex? A simplex S is the convex hull of the elements in X. So with this definition, is delta n a simplex? Well, one way to look at it is the following. I can take the set, so I can show here first that the set X is just basically my coordinate vectors equals 1 to some d. And these are linearly independent. So in particular, 1 minus any, if I take this set and subtract any one element, the remaining set is still linearly independent. So this set is still affinely independent as well. And then we're basically saying that we already said that this is a convex set. It's the convex hull, all possible convex combinations of these unit vectors. So it is in fact a simplex. Is it clear at all to you guys why a simplex might be important if you're trying to model things using these probability distributions? Like we were talking about, you have these ontological models, and I sort of threw a bunch of jargon at you. But the underlying sort of geometry is very related to simplices. So one thing that you might want to do is say that you have some lambda, which is a set of ontic states, right? So this is just like some set of physical observables. And I want to take lambda and map it to some real vector space that has the size of lambda. So this will work if it's a finite set. So what do I mean here? What do I mean here? How does that work? I take some lambda, maybe this, and I map it to some coordinate vector where E lambda j is equal to 1 if j equals lambda, and 0 else. So what am I doing? I'm basically just, I can think of the n simplex here as being, these n's are my different outcomes. These are my different ontic states. Or conversely, take some set of ontic states, and then you map them to a real vector space where I label the Cartesian coordinates by these lambdas. And then the probability distributions over lambda are precisely the convex combinations that you have here. These are non-negative, they sum to 1. Therefore, when I do this mapping and then I look at any possible convex combination of these, I can interpret those as probability distributions over lambda. Let's make it just a little bit more concrete.
Or is the definition of the simplex that it's finally independent and the convex?
Yes, you take an affinely independent set, and then you take its convex hull. So in particular, what the affine independence guarantees is that these points that are in here are actually extreme points. So because I could imagine taking the following set of points, 1, 2, 3, all collinear, right? Well, they won't all be extreme points of the convex set, which is just the interior here. So the affine independence guarantees that if I want to talk about these as being different outcomes, I really want them to actually be independent of each other. Okay, so I want to make this map just a little bit more clear. So what I would like to do is say that I have some probability some point P. P is inside of the simplex, and so I write P suggestively in this way, lambda. So I am labeling the points, this is a finite set. Maybe I'll just use I for a second, and then we'll reestablish the connection here. So Pi, Ei. So, and then this is required to be a convex combination. So this thing is a point. These are vectors, right? But what we do is we make this connection between the coefficients and probability distributions over I. So if instead I have, I've labeled my unit vectors in terms of lambda, then I would say that P is equal to a sum over lambda, P of lambda, E lambda. These are just unit vectors. I just wrote the same thing. I'm just sort of putting a little bit of interpretation onto it. And then this thing is precisely the kind of object that shows up when we talk about preparations being something like P of lambda given P. These are the kinds of, it's the coefficients of something like this, geometrically, mathematically, that show up as being a representation of these preparations on the operational or interpretational side. So there's a sort of tight sort of mathematical link that you can make between these things. And the fact there's a lot of sort of special properties of simplices that end up making it a very rigid structure. And quantum theory deviates from that very much. And one thing that I will talk about probably next is that if you have a point in a simplex, it ends up being, this set of coefficients ends up being unique, precisely because of the affine independence. Whereas, what we can say about quantum states is that a representation of a particular mixed state might not have a unique representation. You only see the density operator, but that density operator could come from many different ways of mixing pure states. So that's one sort of significant qualitative and quantitative sort of departure between classical theories and quantum theories. What else did I want to say about this? Yeah, so I guess the sort of simplest picture, I'll just do a couple of the examples, right? The indexing, I call something a 2 simplex if it has 2 outcomes. No, I call, okay, for n equals 2, it's called a 1 simplex. Why? Because actually you have something that's like this and it's 1-dimensional. So this is a 1 simplex. But you get a 1 simplex when you have 2 outcomes. So if I think of flipping a coin, this is the geometric representation. 50-50 is here, and weighted is on either side. I can think of this as being 0, 1 as vectors. And then I can have my 50-50 fair coin, say fair. P fair is equal to 1/2 0 vector plus 1/2 1 vector. Now, n is equal to 3. Better to draw this maybe like this. So I take my unit vectors, 1, 2, 3. And my simplex will be this shaded region. So this is a 2 simplex because the dimension of the corresponding affine subspace is 2-dimensional. It's like a plane within 3 dimensions. And so this is going to count if you have a, let's see, a three-sided die, which is just basically counting 1 and 2 together, 3 and 4 together, 5 and 6 together. You would represent it by precisely a geometric shape like this. Okay, here's another interesting thing about simplices, which is that if you say that one of the probabilities is, if you say the probability of one of these outcomes is 0, what does that imply geometrically? Say I have a point P, okay, P is equal to, it's got 0 on the first, and then it's got non-negative stuff to Pn. So P is still inside of a simplex, but it's on a face of the simplex. And what's special about this face of a simplex? This is a 2-dimensional simplex. The faces are the lines that bound it. These are also simplices. If I set one of these to 0, what I'm saying is that I still have a probability distribution on the remaining outcomes. So if I say something like, I have this 3-sided die, and I know for a fact that it never goes on sides 1 and 2 together, or, I was talking about the actual die, but say one of the outcomes never occurs, then you're restricted to a one simplex spanned by the two other outcomes. So the faces of a simplex are always a simplex of lower dimension.
What is the sense of defining something that never happens? I mean, like, how would you then have this two-dimensional
Okay.
simplex?
Well, it might be the case that for a certain preparation, that never happens, but for another preparation, it does. Like, you might say that one preparation is going to be, one preparation is I take the dye and I throw it in an oven and I read the outcome. It's going to be completely thermal, random. I get any outcome with with almost equal probability. And then the other preparation is I put it on the table. So while it's true that in a particular preparation you would only get a subset of outcomes, it's still worthwhile to define it within the scope of the larger geometric simplex.
What was the lambda again?
The lambda is basically, lambda is just our coordinates for our simplex, essentially. You can think of it interpretationally in this way. These are like the ontic states. Sorry, I'm trying to go. Okay, you are asking the physical interpretation are these ontic states. When I define my ontological model, these lambdas are precisely the physical states, and so now I have some sort of, and then I establish this correspondence between the lambdas and these vectors in Rn, and that's how I sort of start to geometrically represent these ontological models. If you want to show that if I have some point P that's in a simplex, show that P equals sum I, lambda I, well, it could be any, actually. Vi is, and I should, I guess, just, this is a convex combination, so equals 1. This guy is the convex hull of these V's. So if I were to ask you, okay, show that this convex combination is unique, how would you go about doing it? Or what's like a good first step?
You would assume that there is another combination and then charge that contradiction to, I guess, either the conditions on the lambdas or maybe on the
Yeah, that's exactly right. So I will take it to be some Qi Vi, right? Does this exist? Is there some other one? So what I'll say is the following, is consider, say that this set goes from 0 to D. Okay, let's go with that. So I will consider the following point, V0, P minus V0. And what we know is that if this set is affinely independent, then the set of VI's minus V0 is linearly independent. So what that means in particular is that, let's define the following point before I do that. Let's just define Y as being equal to I equals to 1 to D of lambda I of VI minus, V0. let me see if I want to start like this. Do I want to assume something else here? What I want to do is use the fact that vi minus v0 is a linear combination. So, okay, actually what I want to do is the following, I guess. Okay. So, let y be equal to any arbitrary linear combination, alpha I of vi minus v0. And this goes from 1 to d. This is going to be I equals 1 to d of alpha I vi minus sum I equals 1 to d alpha I v0. And I think now I say that this y is equal to, okay, so I say that y is equal to, maybe I was right to just write this down in the first place, p minus v0. P minus v0 must be in the linear span of the remaining vectors, and so I write this down as being equal to I equals 1 to d of alpha I vi minus, let's do plus minus I equals 1 to d alpha I v0 plus y, so p is equal to sum equals 1 to d of I plus 1 to d alpha I v0. Yeah, so this would only work for, this would work for any affine combination. And so I think the fact that, so I have to actually start from, sorry, I'm recreating what I thought the solution was. I think that I'm starting from precisely this equation. So maybe it was like this. Start from p minus v0, then what this is going to be equal to sum I equals 0 to d of lambda I, and maybe I'll separate this out. So you have lambda 0, v0 minus v0 plus lambda I equals 1 to d lambda I I want to vi 1 over lambda 0 over lambda I v0. Sorry, 1 second. Let me get my bearings around me. Okay, so this solution works for affine combination because I have this as a linear combination. Is it valid to just say, but what I actually wanted to do was say I have this, maybe another approach. Let me think for a second. Maybe another approach is better. So I say that there exists another solution, and then since these are equal to each other, I say that these are equal to each other. I subtract on both sides by some element v0. Yeah, I don't know. There's something tricky about the coefficients, but the idea would be to subtract on each side by like some v0, and then that part, there should be a part of that that's linearly independent, and then I set those lambdas and q's equal to 0 for the translated space, but somehow I'm not seeing how I did the coefficients now. Let me see if I... I think I have this worked out somewhere. Then this decomposition is unique. Oh, actually, you know what? I think another way to look at it is the following. Okay, so, and I think I already did this before. So I have that this thing, y is given by a unique linear combination in terms of these alphas. And then essentially, this tells me that I have a unique affine combination, or hold on. This is y. Y is equivalent to this. And then p, I added p to both. Sorry, this is 1 minus. Okay, no, this is the correct one. Okay, good. This is correct, and this is showing that there's a unique affine, there's a unique solution in terms of the affine hull. But if there's a unique solution in the affine hull, then there's also a unique convex solution if it exists. So if you are guaranteed, so I already said that P is inside of the simplex. So if it's inside the simplex and there's a unique affine combination, then using the fact that you know that it's in here means that there's a unique convex combination. So I think that that's the argument. Sorry about that. You are guaranteed, you're told that P is inside the simplex. So you have uniqueness, and the fact that it's inside the simplex means that there exists, that these alphas must be non-negative.